Hello my dear students, I warmly welcome you to Sia's digital classes. In this lecture, we are going to discuss about one of the important theorem, that is normal subgroup test. Okay, so this theorem is the fundamental theorem for the all upcoming theorems from Unit-3. So first of all, see the statement of this theorem. Name of the theorem is normal subgroup test. Okay, in the name only clearly we have this theorem is totally depending upon the normal subgroup. Normal subgroup is the new topic. Okay, so we are going to discussing from today only. First of all, see the statement of the theorem. Define normal subgroup. Prove that a subgroup capital H of a group capital G is normal. Okay, so we are taking that a subgroup capital H. Okay, so a subgroup capital H of a group capital G is a subgroup. That subgroup is normal. Okay, if and only if we have to prove this condition. Small h capital H x inverse belongs to, is subset are equal to capital H. If and only if we have to prove that xh x inverse subset are equal to capital H. Okay, so this is the statement of the theorem. Capital H is normal if and only if xh x inverse subset are equal to capital H. So before going to prove this theorem, so why we are studying this normal subgroup test? What is the reason behind this theorem? Okay, in the previous lecture we discussed a theorem based on the properties of cosets. Okay, where we discussed that one of the property, that is second property of the cosets. What is the second property? So you can clearly note that A into H is equal to H if and only if A belongs to capital H. Okay, so this is the second property of the cosets. A into H is equal to H whenever A belongs to capital H. So this property is not true for all A belongs to capital H. Okay, for every time whenever you take small a belongs to capital H, this condition A into H is equal to H is not true. Okay, this statement first of all was discovered by the famous mathematician Galice. Okay, so in the beginning of the 19th century, that is in the time of 1815 1820 around, the famous mathematician Galice was discovers that A into H is equal to H is not true for all A belongs to capital G. There is some minute mistake, there is some minute error in that statement. Okay, that statement here we are going to study as a weaker statement. Okay, that is the statement of A into H. Okay, so this is the statement of the cosets. A into H is equal to H into A if and only if H is equal to AH A inverse. This is the sixth statement of the coset property. Okay, sixth statement of the coset property. A into H is equal to H into A if and only if H is equal to AH A inverse. This is the pure statement. In this statement there are some minute error. That error we are going to study in the form of normal subgroup. Okay, that error first of all was discovered by the famous mathematician Galice. Okay, so now you can see what was that error. So that is the definition of the normal subgroup. A subgroup capital H of a group capital G is said to be normal subgroup of capital G if A into H is equal to H into A for all A belongs to capital G. I clearly mention you. Okay, A into H is equal to H into A is not true for every small a belongs to capital G. Okay, but in this definition what we are going to study that A into H is equal to H into A is true for every small a belongs to capital G whenever for small h belongs to capital H and small x2 belongs to capital G, x h x inverse belongs to capital H. Whenever this equation number 1 holds, then A into H is equal to H into A. That is the sixth property of the cosets. Okay, that will become the perfect. Okay, so therefore it is denoted by the normal subgroup is denoted by capital H is triangle to capital G. Okay, you no need to read it is the triangle, so you have to read it as capital H is normal subgroup to capital G. You have to read in the words format. That symbol also you have to read it as a normal subgroup. Capital H is a normal subgroup for capital G. You know very well the subgroup notation. Capital H is less than or equal to capital G. This is the subgroup notation. Capital H is less than or equal to capital G means capital H is a subgroup of capital G. Now remove that equal symbol. Okay, So remove that equal symbol. Okay, so you can clearly add here that symbol, then it will give the normal subgroup symbol. So this is the definition. Here equation 1 is the weaker version of the one of the cosets property, that is A into H is equal to H into A if and only if H is equal to AH A inverse. That is the sixth property. Okay, so that is the sixth property, sixth coset property. Okay, so now this is the definition of the normal subgroup. Now we are entering into the proof of the theorem, that is capital H is normal. Basically that capital H is a subgroup. That subgroup we are going to prove that normal subgroup whenever x, h, x inverse subset are equal to capital H. That is the theorem. So now here if and only if condition is there, we are going to prove this theorem in the two steps. The first step is necessary condition. Okay, and the second step is converse part, that is sufficient condition. So now proof, let capital G be a group. Okay, from the given statement, and capital H be a subgroup of capital G. First of all, I am taking that capital H be a subgroup of capital G. So now with the help of that subgroup, we are going to prove that capital H is satisfying the given theorem. So this is, you can also write it as a claim. Claim is nothing but what we have to prove in the theorem. Capital H is normal if and only if H x x inverse subset are equal to capital H. So now necessary condition. In necessary condition, I am taking LHS part of if and only if. Okay, by taking LHS part, that is if subgroup capital H is normal, I am taking this LHS part. Okay, for if and only if I am taking this LHS part. After taking that LHS part, we have to prove the RHS part in necessary condition. So then by the definition of normal subgroup, you can write A into H is equal to H into A for all A belongs to capital G, and x h x inverse belongs to capital G whenever small x belongs to capital G and small h belongs to capital H. Okay, now in necessary condition, to prove the given theorem, it is enough to show that we have to prove this condition. This is the RHS of the given theorem. H x x h x inverse subset are equal to capital H. To prove that condition, now I am considering one equation. Okay, so x h x inverse, the set format for that x h x inverse. Okay, so the set format is x h x inverse such that where small x belongs to capital G, small h belongs to capital H, this set is always subset are equal to capital H. And next, and again I am considering that x inverse capital H x is equal to, in previously we considered that x h x inverse, now we are x inverse h x. Okay, so this is also another set. That set I am taking subset are equal to capital H, where capital H is a normal subgroup. Why? Because we are taking directly capital H is a normal. Whenever you take capital H is a normal, then you have to use the definition of the normal subgroup by using equation number 1. According to that equation number 1 only, we are writing these two equations. Okay, that is we are giving that equation number 2. Okay, so now it is clear from equation number 2, x inverse hx is subset are equal to capital H. Okay, after taking equation number 3, now pre-multiply on both sides with small x. Okay, here I am multiplying, pre-multiply with small x on both sides, then you will get this step, x into x inverse hx subset are equal to xh. Now according to the inverse property in group, x into x inverse is equal to identity element, and identity into something, again you will get something. Okay, so h into x subset are equal to x into h. So after getting that condition, okay, so again post multiply with x inverse on both sides. So first we did pre-multiplication with x, now we are doing post multiplication with x inverse on both sides. So therefore again you have to apply the same inverse property, then you will get the identity element. So therefore capital H is subset are equal to xh x inverse, that is taken as equation number 4. Here if you observe carefully from equation number 3 and equation number 4, okay, x inverse hx subset are equal to capital H, h subset are equal to xh x inverse. So therefore from by mixing both of the equations, you will write x h x inverse is equal to capital H. Why? Because whenever you write a subset are equal to b, b subset are equal to a, then clearly you can write a is equal to b. So by using that condition, we are writing x h x inverse is equal to capital H. So that is the right hand side condition of the given theorem. That is the necessary part. Now, insufficient part. Sufficient part is nothing but conversely. Conversely, I am taking that if x h x inverse subset are equal to capital H, that is taken as equation number 5. Okay. Converse part I am taking right hand side part. We have to prove that left hand side. What is the left hand part? H is normal in capital G. We have to prove that condition. To prove that condition, H is normal. So letting x is equal to small a in equation number 5. This is the equation number 5. Or you can call it as a inequality. So therefore, if you substitute x is equal to small a, then it will become in this format. A inverse subset are equal to capital H. Again, post multiply on both sides with small a. Again, do the post multiplication on both sides with small a. Then you will get that same inverse condition identity element. So you will get equation number 6. A into H subset are equal to H into A. Now, letting x into x equal to A inverse in equation number 5. In the equation number 5, wherever you have small x, substitute A inverse. Then you will get this equation. A inverse H, A inverse whole inverse subset are equal to capital H. So now, by simplifying that, you will get this one. Now here, pre-multiply with small a on both sides. Okay, post multiply with A inverse, pre-multiply with small a on both sides. Then you will get that given. So this condition, H into A subset are equal to A into H, that is taken as equation number 7. Okay. So in this theorem, each and every equation has one significance. That's why we are giving that equation numbers up to 7. Okay. So therefore, from equation 6 and equation number 7, we can clearly say that A into H is equal to H into A for all A belongs to capital G. This is the original definition of the normal subgroup. Okay. So this is the condition of the normal subgroup from equation number 1. Okay. So therefore, H is normal. Whenever A into H is equal to H into A for all A belongs to Z, whenever it holds, actually it is a weaker version. When it will become stronger version, okay, X inverse also belongs to capital H. So then it will become a stronger version. So therefore, so that is the difference between the weaker version and stronger version of the sixth property of the coset. So therefore, hence a subgroup capital H of a group G is a normal subgroup if X inverse is subset are equal to capital H. Here usually you will get one doubt. That means here we have to prove X inverse is subset are equal to capital H. But here we proved that X inverse equal to H. What is the difference between these two terms? Here clearly we have subset are equal to. Okay. So we proved that equal. Okay. Then automatically it will become a subset. So therefore, this is the proof of the normal subgroup test. This is the first theorem. Okay. In unit number 3. This theorem we can applicable in the next upcoming theorems. Okay. So make a perfect practice. Prepare well. So until bye. Thank you.